like think of it as a simulator. Okay.
Mm-hmm.
All right. She's yours. You can start whenever.
Okay. Where's my earphone here? I'm online then. Right,
Yes.
yeah, lovely. Okay. Good afternoon, everybody. My name is Kieran, and today we're going to be learning about matter and change. Our objectives for the day are to identify the properties of matter as extensive or intensive, and also to define physical property and to list several common physical properties of substances. And also to differentiate among three states of matter, only three. And we'll also learn to describe a physical change. Now, what is matter? As defined here, matter is anything that A, has mass, and B, takes up space, so a certain amount of room. Mass is a measure of the amount of stuff or material that an object contains. Now, this is very different. It's often confused with weight, but weight is different. Weight is a measure of the gravitational force on something. Now, volume. I'm sure you've heard this one before. Volume is a measure of the space occupied by the object. A measure of the space occupied by the object. Say, if we were talking about water, the volume in a bottle such as this would be about 0.7 of a litre, I believe, or 700 mil. Now, where are we? Describing matter. Properties used to describe matter can be classified as extensive, which depends on the amount of matter in the sample, mass, volume, calories. I gave you an example of the volume. The mass, the calories is the amount of energy in a food, for example. Intensive depends on the type of matter and not the amount present. We might come back to this in a moment, actually. So the hardness, the density, how much it weighs per cubic meter, for example, the boiling point. As I'm sure we all know, boiling point of water, 100 degrees Celsius. Now, properties are words that describe matter. Now we use adjectives to describe matter. Physical properties. A property that can be observed and measured without changing the material's composition. Now, obvious ones here, examples are colour, hardness, and pressure of matter. Let me give you some examples later of those. Chemical properties, a property that can only be observed by changing the composition of the material. So examples here again, the ability to burn, ability to burn, so coal, oil, obviously have a strong ability to burn. Decompose, oh, that's a hard one. Decompose, you can think about the leaves that fall from a tree onto the ground. They get wet, they start to rot, decompose. Fermentation will be used to make alcohol, for example, ethanol. Ability to react with, we all know that certain chemicals react at a different rate with each other. Now, the states of matter, important. A solid, just a moment. Excuse me. Sorry, can they answer questions?
Yeah, don't type in the box.
Yeah.
They'll ask.
If I ask them a question, they'll just type in as a yeah, cool. Okay. I'll get some examples from you guys, I think. So solid, matter that cannot flow, cannot move around. So it has a definite shape and a definite volume. It takes up a certain amount of space. Can anyone give me an example of a solid that we have in front of us now? Anyone give me an example? You have a desk in front of you. Iron, yeah, iron. In certain forms, at certain temperatures, iron, yeah, like if you've got an iron table, it's a solid. Any more? What are you working on now? What are you typing your answers into? You're working on a keyboard. It's a solid. As we said before, the matter cannot flow in the keyboard as it is now. It has a shape. It's kind of rectangle and flat. The second one, liquid. Now, liquid has a definite volume, as we talked about with the water, but it takes the shape of its container. It flows. So if you think about it, you've got the water in the bottle. If you have a jug, you pour the water into the jug. The water becomes the same shape as the jug, doesn't it?
Yeah.
And gas, a substance without definite volume or shape, and it can flow, so it can move around, change its shape. Anyone give me an example of a gas? A gas. O2 is a gas, yeah, exactly. You could even just say air. Air is a gas, or it's many different gases together. But as you know, it doesn't have a definite volume or shape. It can flow. It can move around. I'm not sure if we have this later on. The volume of a gas will basically depend upon the container that it's in, rather than the amount of gas that's in there. Where are we? Vapor. Oh yeah, vapor. A substance that is currently a gas, but normally is a liquid or solid at room temperature. So, which is correct? Water gas or water vapor? So water is usually at room temperature anyway. It's a liquid, isn't it? So normally a liquid. When we put it into a kettle to make a cup of coffee or tea, it gets to 100 degrees and it becomes water vapor. Now, all liquids will have a point at which they become the vapor or their gas form. We'll move on to the next page. Where are we? Okay. This is a nice table. So solids. Solids, your iron table, your wooden table, your plastic keyboard. Definite volume. So the volume does not change. It stays the same as long as the temperature and the conditions stay the same. A definite shape. Absolutely, yes. Again, you don't change the conditions. The shape will stay the same. The table doesn't become round if it's a square. Result of a temperature increase. Anyone know what that word should be? We'd say a small expansion. Expansion. E-X-P-A-N-S-I-O-N. Now, I'm sure you would have come across this before. As you know, if you increase the temperature, most things will get bigger by a very small amount, even yourself. Most matter will expand with temperature. Will it compress? So will it compress? Can you make it smaller by pressing it? If it's a true solid, I mean, I suppose you could with a lot of pressure, but a table between your hands, it's not going to compress. Same with your keyboard, unless you're really strong, you're not going to be able to compress it. A liquid, again, definite volume. Volume doesn't change unless. So you pour your water into a jug, the volume is exactly the same. It doesn't change unless you spill some, of course. Definite shape. Does the shape stay the same? As we said before, no, it doesn't, does it? It becomes the shape of the jug if you pour it into the jug. Now, the result of a temperature increase. Again, we would see a small expansion. One example is, I suppose you could use, again, if you boil your water, it's gonna change volume a very little bit. It's going to expand. Same with the ocean. The increase in the temperature in the atmosphere, it causes a very, very small expansion of the ocean, so the sea level would rise just a little bit. And liquid, will it compress? Will it compress? Again, no, same as a solid. You can't pressurize it the way that you can a gas. And a gas, does it have definite volume? No, absolutely not. A gas will spread out to the volume of the container. One example is a balloon. If you blow up a balloon, you put one lungful of air into the balloon. It's gonna the stronger the rubber of the balloon, the less it will expand. But an airbag, the gas will expand to the size of the airbag. Definite shape. Does the shape stay the same? No. Again, the gas will expand to the size of whatever is containing it. If you have a heart-shaped balloon, the gas will take the shape of a heart shape. If you have a round balloon, the gas will take the shape of the round balloon. The result of a temperature increase. Gas different to solids and liquids. If you heat the gas, you would see a large expansion of the matter. Basically, I'm not sure if this has gone over later on, but with the gas, the particles that make up the gas, they're moving around a lot more than in a solid. In a solid, they're set. They don't move around very much. They'll vibrate, but they won't change position. In a liquid, they will change position quite a lot, which is why you can put your hand into it. The water will move apart to fit your hand into it. A gas, they're moving around very fast in all different directions, and if you heat them, it will just make them expand much more than you see in a liquid or in a solid. Will it compress? My mouse has stopped working again. Oh, here we go. Gas will compress. We gave an example a little while ago of that, didn't we? Can you give me an example, anybody? Will gas compress? And how will it compress? How can we compress it? I've got on the top of my screen public message. Waiting. Does that mean someone's trying to?
This is that is in the chat. Don't worry about it.
All right.
Don't mind it.
Okay. Okay, will it compress? Of course, yeah. A balloon, an airbag. Another example would be a car tire, I suppose. You pump air into the tire. If you only pump a little bit in, the tire would be very soft. You could push it with your hands together. If you put a lot of gas into the tire, air, the tire would become a lot harder. It would become hard, you punch it, hurt your hand. So yeah, that would be a compressed gas inside the car tire. And the next one, aha. The fourth state of matter would be a plasma. Now, this is not common on the Earth. You can see it in the atmosphere sometimes, but plasma is formed at high temperatures, very, very, very high temperatures. The ionized phase of matter, and you'll find it in the sun. You look at a photograph of the sun, you can see all of the different waves, or it looks like it's spitting out all of the matter. This stuff there is plasma. It's become ionized just because of the really high temperatures and pressures in the center as well. Where are we here? And you'll see here with the solid, it's like a little Rubik's cube or something here. But all of the particles are very tightly packed together, and like I said, they will vibrate. Like all matter moves around to a certain extent, but in your solids it doesn't move too much. It can't change position. And in your liquid, nice little drawing of orange water in a jug. You can imagine, well, you can see that the particles will actually move around in there. We need a little graphic there to move them around, but you can visualize it with water. You put your hand in it, the particles of the water will move around. Gas, as you can see here, they're a lot further apart, the particles here, than in a liquid. And as we said, they'll expand to the edges of the container. They'll expand as far as they can, basically, until something stops them. And this is your plasma. Complicated subject. I'm sure we're not going to do much more on that today. We do actually have examples of plasma on the Earth. We use it in neon lights For example, the lights you'll see above shop windows, neon, that's actually a plasma. But yeah, there are not many examples on the Earth.
ก็บอกว่ามีอะไรให้มันถามอีกเป็นเรื่อง operation นะครับ
Now we see again the three main phases. The fourth is obviously plasma, but that's a whole other lesson. The three main phases, page 41 of your books. You'll see again here, this is a type of rock, crystallized rock. I'm not sure which rock it is, or metal. My eyes are not too good. Anyway, as you see here, the particles in the solid, they're very tightly packed together. Again here, in the liquid, they're not as tightly packed. They will move around more freely. And in your bottle of gas here, I'm not sure what gas that is, but you'll see they're a lot further apart, and you can't see it here, but they will be moving around a lot faster than the particles in the liquid, and especially in the solid. Did I have anything else on that? I don't think I did. The changes of state. You know all of these words, I would have thought. Freeze, melt, condense, and evaporate. There is another one that I'll give you as well. But, so freeze is an obvious one. We can freeze water into ice. Water's a good example actually. When you freeze water, it's one of only a few things that actually gets bigger as you freeze it. Do you remember most things, if we heat them, they become bigger, they expand. In the case of water, if you freeze it, it becomes bigger as well. The particles move further apart. But condense is when a gas turns to a liquid. Can you think of any examples of that? When does a gas condense into a liquid? If you're close to a window, you can look out your window. And you can actually see the clouds, can't you? That is actually a case of water, vapor, condensing to become a liquid, ready to fall on us and cause even more floods or to water the crops. Melt, again, we'll go with waters. If you take the ice out of a freezer, put it into a glass of orange juice, it will warm it, the ice will melt. Most solid, if you think of iron as well, the example from earlier, iron itself would have a melting point. It's a lot higher than the water melting point, which, as we said, 100 degrees. Iron would probably be 7 or 8 times that. I can't remember now, but most solids will also have a melting point. Metals, rocks even will have a melting point. Evaporation. As matter would have a melting point, it would also have an evaporation point. For water, again, 100 degrees. For a metal or a rock, again, it would be higher, much higher, wouldn't it? Just have a look at the next page briefly. No, it's not going to be there. There's another word I think is useful to you, sublimate. We'll not go right into it, but this happens to ice as well, water ice. It actually goes through a phase. It misses out the liquid stage entirely. It'll sublimate from the solid straight away into the gas. This happens in the North Pole, the South Pole. I'm sure that word is in your textbook. I believe it was. I saw it earlier. But yeah, sublimation. The ice sublimates. Copper. Now I'm sure you know from your chemistry classes, copper is a type of metal. We have a molecule chamber here. And the copper phase, it's solid. So anything less than 1083 degrees C, it would be in its solid state, its solid form. And on the next page, liquid. So the copper would actually become a liquid between these two temperatures, so 1083 and 2594 degrees C, very hot. The copper would be a liquid. And you can see here the molecules they're a lot further apart. They're moving around freely. Now the vapor stage of copper. You wouldn't see this except in a laboratory on Earth, I wouldn't have thought. Underground, it probably would reach that temperature deep down, but over 2595 degrees C, you'll see here the particles are a long way apart here. They're moving around really fast. And it's in its gas form. I'm not sure in your textbooks if you'll have a table, but very interesting to see the different temperatures, the different elements, different molecules, where they reach the liquid and vapor stage. I didn't see one. We'll leave that anyway. Okay, next. Physical versus chemical change. Physical change will change the visible appearance without changing the composition of the material. So you can boil water, it won't actually change it, it will still be water. It will still be the same molecule. Same with melting. You can melt copper, it will still be the same basic chemical makeup. Cut things, bend things, split things, or crack them. Physical changes that don't change the composition of the material. Is boiled water still water? As we just said, yeah, of course it is. And it can be reversible, tough word, or irreversible. So if you boil water, is it reversible? Can it go back to being cold water? Of course it can. Of course it can. Or irreversible, something that can't be changed back. So a physical change can be either reversible or irreversible. Now, a chemical change is a change where a new form of matter is formed. Again, we've used these words before. Rust. Rust. Now, where would you see a rust? Checking that you know these words. Rust. There's a lot of cars in Bangkok at the moment with some rust on them, I'd have thought, after all of the water they've been driving through. Rust happens to one example, oxidation to iron. If you leave iron out in the rain, it's going to rust, it's going to go orange, and it's going to eat away at the metal. So a change where a new form of matter is formed. Yeah, rusted iron, different sort of matter, different chemical composition. Burn, if you burn something, obviously, it's a new form of matter. Take a slice of bread, put it into a fire, burn it, it's going to be completely different. It's just going to be black powder. So it's a different form of matter, a new form of matter. Again, decompose. If a leaf falls from a tree, it sits in the bottom of the forest for weeks and weeks, gets rained on, it's going to decompose. It's not going to be a leaf any longer. It's not going to have the same composition. Decompose. And ferment, again, it changes the chemical makeup of matter. If you ferment fruit, the chemicals left in the matter after it's fermented, totally different, totally different. Apples turn to cider. We'll go to the next page. The next section. Okay, section 2.2, objectives. Categorize a sample of matter as a substance or a mixture. And distinguish between homogeneous and heterogeneous samples of matter. How do you tell them apart? And describe 2 ways that components of mixtures can be separated. Definitions here. Mixtures are a physical blend of at least 2 substances. Have variable composition. They can be either heterogeneous, where the mixture is not uniform in composition. Not uniform, it's not the same all the way through. Chocolate chip cookie, it's not the same all the way through, is it? Gravel, made up of many different types of rock, stone. Soil also, made up of silicates and all sorts of different chemicals. It's not uniform, it's not the same all the way through. Homogeneous has the same composition throughout. We call these solutions. Kool-Aid. Air, as we said earlier, the air that we breathe, it's not just oxygen, is it? It's made up of many different gases. Salt water. If you get a spoonful of salt, put it into some water, stir it around with a spoon. The salt's going to dissolve and become a solution. Same with sugar in your coffee. You can't see the sugar, it's become part of the solution. But every part, again, it keeps its own properties. The sugar is still the sugar, the salt is still the salt. And where are we now? Solutions are homogeneous mixtures. So, mixed molecule by molecule, that's too small to see the different parts. They can occur between any state of matter. Gas in gas, nitrogen and oxygen. Liquid in a gas in liquid. Where do we see that? Gas in liquid, you get carbon dioxide in the sea. Solid in liquid. We said about that before. Solid in solid. Alloys. If you've got a table with metal legs, I'm sure it's not just one type of metal. There's two different types or three different types of metal that go in to make up an alloy. And thus, based on the distribution of their components, mixtures are called homogeneous or heterogeneous.
มีรูปหันเลยเป็นรูปไม่ใช่รูปอาชีพเลย
Phase. Phase. The term phase is used to describe any part of a sample with uniform composition of properties. So a homogeneous mixture consists of a single phase. Heterogeneous mixture consists of two or more phases. Now you've got to figure that on page 45. I don't believe I've got that with me. No. Okay. So a homogeneous mixture, just one phase. Heterogeneous mixture, you've got two or more phases. Is there more on this? I think we'll leave it there. Okay. Separating mixtures. Some can be separated easily by physical means, rocks and marbles. Rocks and marbles, very easy, you separate them using your hands. Iron filings and sulfur. Iron filings and sulfur. You've come across sulfur in your lab classes, I'm sure. If you mix them up, use a magnet, pass the magnet over the top. Iron filings will obviously come up and stick to the magnet. Differences in physical properties can be used to separate mixtures. You'd use that in a chemistry lab as well, I'm sure that filtration. Filtration, you use a filter. It separates a solid from the liquid in a heterogeneous mixture by size. I'll give you an example of a filter. If you're making a cup of coffee, I suppose, you could use that as an example. The granules of the crushed up coffee, you put it into the water, you let it brew for a few minutes, and then you use the filter. You either pull it up or push it down. I've seen both. The filter has very small gaps to allow the liquid to pass through the gaps, but it separates the solid, which is generally bigger than the gaps in the filter. Where else are we? Wow, chromatography. Components of dyes such as ink may be separated by paper chromatography. Now this is a whole lesson on its own. Basically it's going to use the density. The more dense materials are going to fall further down. The less dense material is going to be at the top here, the yellow colour. Now, I think separation of a mixture. Distillation takes advantage of different boiling points. It's a nice looking apparatus. Distillation, we use it for a lot of things. People use it to make alcohol, fuels, distilled water. You'll see here, this is the start. You got the Bunsen burner at the bottom here and the flask above it. The liquid in the flask here is heated to its boiling point. The vapor rises up here and enters into the tube here, and when it's in this little container here, it starts to cool. As we used the example earlier about water vapor in the sky, it's exactly the same concept. The liquid begins to cool until it condenses. It becomes a liquid again. And it ends up dripping down as a liquid again into the flask. And the distillation means that the materials that were in this solution the vapor is obviously pure. So if it's a solution of water and salt, the water vaporizes, leaving the salt in the flask here, and the water that we get out at the end here is pure water, no salt.
Yeah, that was great.
Do we have a little quiz?
No, you don't need to do no quiz. That's it.
Right.
So let's go upstairs and talk about
Okay.
how we're gonna proceed from here.
Okay.
Here, let me take over the